Okay, welcome to lecture. We'll get started here in just a sec. We're continuing on in chapter 11, I think, our last chapter. So like I said, we'll continue on here with this chapter. We'll stop a little bit early, give you a little chance to get set up, and then obviously we have our exam later today, around 9:30 or so, where we usually start, around lab time, 9:45. All right, so we started talking about here the last chapter, and the last chapter deals with kinetics, and kinetics is basically the study of how fast or slow, for example, a reaction does take place. Um, and there's some effects or things that do affect, obviously, how fast or slow a reaction will take place, things like concentration, things like temperature, so there's some other sort of factors, catalysts involved as well. So we started talking about at the beginning here was sometimes referred to as sort of the rate expression. And the rate expression is basically a way that you can compare sort of the average rate for the reaction from sort of beginning to end, and how all the reactants are changing over time, and basically how all the products are changing over time. So that sort of gives us our change in concentration over time, or like molarity over seconds, sort of for the rate. And as we talked about, we basically can use the coefficients there in the balanced equation to help us do that. We basically take 1 over the coefficient, and what that does, like we talked about, is take care of all the sort of mole to mole relationship that you have in an equation, the stoichiometry of it. And it's the change in the concentration of, say, a reactant over a change in time, or a change in concentration of a product over a change in time. The only difference is in terms of the rate expression is, as the reaction proceeds, we expect that the reactants should be decreasing with time. And we do put a negative in front of that 1 over the coefficient for the reactants, again, to imply that their sort of rate is decreasing with time. And on the product side is positive, because it should be increasing with time in terms of products being made. And ultimately what that does is, when we calculate the rate of a reaction, or the average rate of a reaction, that should end up being a positive number. And with that negative sign on the reactant part, because our final concentration of our reactants should be less than our initial, we do end up with a negative number there. So those two negatives turn the rate for the reaction into a positive number, which is what you would expect. On the product side, we don't put the negative there in those sort of expressions, again, because our final concentration there actually should be larger than our initial concentration, and thus we do end up with a positive rate in that case. So that allowed us, really with sort of minimal information, to be able to calculate sort of how everybody's changing in a reaction. If you know just really information about one thing in that equation, you pretty much can figure out how the reactants are changing, how the products are changing over time. So if you know just how a product is changing, you can figure out how other products are changing. You can also figure out how reactants are changing. You can also figure out the overall average rate as well, and vice versa as well. If you know something about a reactant, you can do the same thing. And obviously, if you know the average rate, you can figure out how everybody is changing sort of with time. That then led us into sort of a conversation here about actual rate law, which is slightly different than the rate expression that we talked about at the beginning. The rate law here really does deal with, and as you can see in the middle of the screen there, is sort of generically written like the rate equals k, a to the x, and b to the y. And the first important sort of difference between the rate expression and the rate law is the idea that the rate law, which is what we're talking about here, only deals with reactants. So the reactants are really doing the important things in terms of the rate of the reaction. So no products are ever found there in the rate law. And what we have is the rate is equal to k. That little k, lowercase k there, is the rate constant. sort of how fast, if you want to think about the reactions proceeding. The concentration is usually molarity, and X and Y are orders, and orders are found sort of experimentally. Um, and they're not the coefficients in the balance equation. So that's something different. We just don't take the coefficients and we use them as those exponents. They do have to be found experimentally. The orders and stuff you can kind of think about as sort of the proportion that's needed to sort of maintain a particular rate for a reaction to take place. You can figure out the overall order by adding those together, and I'll give you the overall order of the reaction. Now, because these things are found experimentally, what that usually means, as we talked about, I think at the end last time, was typically speaking, you'll be given a table. And in that table, usually there's a few pieces of information given to you. It's a table usually of multiple sort of experimental sort of trials or runs. And in that sort of experimental trial and runs in that table, you're typically given the concentrations of the reactants. So all the reactants are typically given to you in terms of their molarity. And the other thing that you're typically given is sort of the initial rate that occurs for those individual sort of trials that are done in an experiment. And you could use that information and sort of take a mathematical approach to help you determine, first off, really the orders of a reaction, that X and Y. And once you sort of do that sort of mathematically and determine the X and the Y values here, that will allow you really to figure out the completed rate law. And once you do that, you then could go back and basically figure out the rate constant, or the value of the rate constant for that particular reaction. So mathematically is usually the approach that most people take to sort of do that, and sort of the equation, or sort of the formula, if you will, to sort of do that is found top left there of the screen. And that is the rate 2 over rate 1 equals k to the a to the x and b to the y. And basically what that means is you go to that table and you basically pick 2 entries from that table. And the 2 entries from that table will allow you to basically figure out either x or y, for example. When you're choosing those entries, again, as we talked about last time, it's not like just take the first one, the second one. It just basically means take 2 entries in the table, and really what you're looking for is one entry where a concentration basically varies, and the other entry as well where it stays the same. So you want to have sort of only one unknown. So like in a math problem, you don't want a lot of unknowns. So we're looking to keep the unknowns to a minimum. So you want sort of one unknown and one unknown, and that'll allow you to solve it. So what you're really looking for is an area where the concentration of one reactant remains constant, the other reactant varies. And typically speaking, if you sort of put the larger rate on top there, where it says rate 2, usually what you'll get is sort of whole numbers, or closer to whole numbers usually. So it sometimes makes the math part easy. It doesn't have to be that way, but sometimes it's a little bit easier to visualize what the answer would be. So let's actually look at sort of an example sort of table and kind of go through the calculation here together to sort of see what would typically occur. So this table here is a typical sort of table for a reaction such as the one there. And again, because the rate law is really found experimentally, it is really common that these type of tables are the ones that you sort of come across. So the first thing that we could do is really just write the sort of generic rate law for this, and that would be that the rate equals K times the concentration of F2 to the X and ClO2 to the Y. And again, as we talked about, only the reactants involved here in our rate law. Again, X and Y are the orders, which is what we're going to try to determine using this table here of the values. And in this particular table, we have 3 different sort of trials. So these would represent 3 sort of experiments or trials that were done in a reaction, 3 times in a row there. And what we're looking for is, again, here 2 entries where one of the concentrations remains the same and the other one varies. So for example, if we did look at experiment 1 and 2 here, what we see is the F2 concentration remains constant, while the ClO2 concentration basically varies. So those would be two good sort of entries to pick from this table. And what we're going to do is basically look at the rates. And usually, like I said, you don't have to do it this way, but usually it'll come out pretty good. A lot better in sort of numbers is I'm going to take the one that has the larger rate, which is entry number 2, and I'm going to put all that information up on top. So for entry number 2, we have a rate of 1 and 2. We have 4.8 times 10 to the minus 3 equals K times our F2, which is 0.1 to the X, and our ClO2, which is 0.04 to the Y. So all this information that I just put on top all came from experiment number 2 in the table. I'm going to go to experiment number 1 and put all that information on the bottom, 1.2 times 10 to the minus 3. K 0.1 to the X and 0.01 to the Y. So this is sort of that setup of the rate 2 over rate 1 formula. And again, obviously you don't want to mix and match. So whatever you choose, whatever entry should all go across the top the same. And everything on the bottom should obviously come from the same entry from the table. So now we could do a little bit of math here. So if we divide these two numbers, we do end up, we end up with a 4. I'll do that math. And that equals, if we come onto this side, now we got K and K on top and on the bottom, and K is the rate constant. So it is a rate constant, which would imply that it is a constant number for that reaction. So although we don't know what it is at this point, we do know it's going to be the same number, which means they are going to cancel out. When we come to the F2 concentration, X on top and X on the bottom is the order with respect to F2. And again, although we don't know what it is at this point, we do know it's going to be the same number, which means these guys will also cancel out. And that leaves us down here at the bottom, where if we divide it, we will end up with 4 to the Y. And at this point, you could hopefully realize that Y will equal 1 in this case, right? If you take 4 to the 1, it equals 4. By the way, if it doesn't come out to a really pretty whole number like this, you essentially can take the natural log of both sides and divide. So you can take like the natural log of 4 equals the natural log of 4 to the Y. And basically, when you do that, you can divide by natural log of 4 to both sides. Those cancel. The Y will come down just to the bottom. And that obviously will give you 1. So a lot of times you could probably just visually look at it and go, I also to the first power or second power, whatever it may be. But if not, you could, one way to do it is take the natural log of both sides and divide. You can also take the regular log of both sides and divide. Either way you want to do it. All right, so now that we figured out Y here is 1, we then want to go back to the table and we want to choose 2 more entries. And we want to do the same thing. We want to choose 2 entries where one remains the same and the other one varies. But at this point, since we kept F2 constant, we now want to keep ClO2 constant, which is our other sort of guy. And in this case, number 1 and number 3 keeps the ClO2 concentration constant. So that's what we're going to put into our thing. So we're going to go with 1 and 3 here. And if we do this again, looking at 1, which is here, and 3, which is down here, I see that number 3 has the larger rate. So again, just to try to get a little bit better whole numbers and stuff like that, I'm going to put that guy up on top. So everything from number 3 will go up on top. And that would get me 2.4 times 10 to the minus 3 equals K 0.2 to the X and 0.01 to the Y. And now I'm going to put everything from entry number 1 on the bottom, which would be 1.2 times 10 to the minus 3 K, and again, that's 0.1 to the X and 0.01 to the Y. So we're going to do kind of the same thing. If we divide here, that's going to be 2. Again, same idea. K, we don't know what it is yet, but K's do cancel. In this case, when we do the division here, we get 2 to the X. And again, over here, as we know, the Y is the same, so those guys are going to cancel. So same idea here. If we solve for it, you can see X is equal to 1. Again, you can take the natural log of both sides and actually divide, and you could get the same answer, or you could visually see this. Any questions on that so far? So again, that's how you could kind of use that rate 2 over rate 1 equation to determine, the orders. So now that we actually do have the orders, we could write the completed rate law. So the completed rate law would be the rate is equal to K times F2 to the first and ClO2 as well to the first. Just like anything else in chemistry, you don't have to put the ones up there on top. It's implied that if you don't see a number, that obviously is 1. And in this case, we could also figure out the overall order of this reaction now. So the overall order would be 1 plus 1, which means it is second order. And the 1 plus 1, it comes from 1 plus 1. The X and Y values is what we add together in this case. If you had 3 of them, X, Y, and Z, you would add together to give you the overall order. Now, once we actually do have the completed rate law here, and what we see from this sort of relationship-wise is as the concentration doubles, so does the rate as well, right? So sort of a 1-to-1 relationship that's happening in this particular one. As the rate quadruples, so does the concentration. So again, it's sort of a 1-to-1 relationship, which is actually where the ones sort of come into play. Now, once we do have, as I mentioned, the actual completed rate law, we could then use it to actually solve for what the value of K would be. So if we take that rate law, which is the rate equals K times F2 and ClO2, and if we solve for K, K would equal the rate divided by F2 and ClO2. And you may ask yourself, okay, so where do I get these numbers from? And where you get these numbers from is the same table that we used earlier. So you could go back to this table. And in this particular case, once you've gotten the completed rate law, it really doesn't matter which entry you choose. You could choose entry number 1 in the table, entry number 2 in the table, entry number 3 in the table. And because it is a rate constant, you should end up with the same value no matter which one that you choose. The only thing that you can't do, obviously, is mix and match, like take the concentrations from one and the rates for the other. If you choose number 1, you have to use, obviously, all the information for number 1. If you choose number 2, you need to use all the information for number 2 and so forth. So for me, I'm just going to choose information from number 1. And if I go back to the table and put in all the information for number 1 into this guy, that would give me 1.2 times 10 to the minus 3 molar seconds divided by 0.1 molar and 0.01 molar. And again, that is all the information that comes from entry number 1 in the table. And if I do all that stuff, 1.2 to the minus 3 divided by 0.1 and divided by 0.01 gives me a rate constant of 1.2. Now, in terms of units, the molarity on top will cancel with a molarity on the bottom, and what that will leave you is 1 over molar seconds as the units, or you could do 1.2 m to the minus 1 s to the minus 1. I can kind of get that in there. Minus 1. So you go either way on that. So this is sort of an example how we could use sort of the experimental information that's typically given to us in these kinetics problems, which is just like this table. You have some concentrations, you have some rates, And again, using the information in the table, figure out the orders for each of the reactants. Once you figure out the orders for each reactant, you'll have the completed rate law, and then you can use the completed rate law to figure out the value of the rate constant. And as we will see later on this chapter, when we see 1/molar seconds, that is a common unit that is associated with a second order reaction. You can actually determine it by looking at the actual units. It tells us a lot about the type of reaction that's occurring. Any questions on any of those steps? So again, sort of visually, you can look at it. If you understand sort of relationships about concentration and rates, you can sort of figure it out non-mathematically. But for us, I would say most of the time, probably mathematically is a better approach. If you choose not to do it mathematically, you do have to sort of, on an exam, sort of label why you did that or explain why you did that. Again, you don't necessarily have to put the largest rate on top. If you don't, it would be okay as well. You just won't get maybe whole numbers or whole-ish type numbers. You might get some decimals, but will come out the same. You just probably have to solve it using that kind of natural log of both sides and divide. All right, so rate laws, as we've seen, a couple important sort of notes on it in terms of calculating it. We are always going to be determining these guys experimentally. So again, on these problems, you'll always have some type of table given to you, that will have a very similar type of information in there. You have to do some calculations to figure it. When we talk about reaction order or the reaction itself in terms of rate laws, typically it is only reactants involved in the rate law, and sort of the order of the reaction is based only on the reactants. Again, they're the ones who are going to come together. They're the ones who are going to determine sort of the rate and how they come together. And the products are just going to be obviously produced. And as we see here in this example as well, the order is not really just the coefficient. For us, it's not that big of an issue because usually by now or something, we talk a lot about equilibrium constant if you take 200B. And when you go to equilibrium constant, you do take the coefficient as the exponent and stuff like that. So here we don't do that. Again, found experimentally. And as you can see here, the coefficient is 2. The order is 1. Although they do match sometimes, but that is not, again, how we get them. It's not just from the coefficient. All right, so I want you to take a second here and calculate the rate constant, the value of the rate constant. If the rate law is the rate is equal to KNO03, if the rate is 6.6 times 10 to the minus 5, when the concentrations are given, what is the value of the rate constant? So take a moment or two and see what you come up with. Okay, so in this particular one, they actually gave us the rate law, so we didn't have to actually calculate it. So here the rate law is the rate is equal to K times NO times O3. And in this particular case, they gave us the rate. They also gave us the concentrations of these guys. So we pretty much just need to rearrange this. So K would equal, in this case, the rate divided by NO times O3. And that would get us 6.60 times 10 to the minus 5 molar seconds divided by our NO, which is 1 times 10 to the minus 6, and our O3, which is 3 times 10 to the minus 6. And looks like we get 2.20 times 10 to the 7. And again, in terms of units here, just like in the last one, the molarity here will cancel. Molarity here will cancel. And we do end up with 1 over molar seconds. Or again, you could do the m to the minus 1, s to the minus 1 in terms of the unit part. This also, again, is the same one that we saw, 1 over molar seconds. And if we look at the overall order here of this reaction, it is 1 plus 1, which would be second order. So again, as you can see, and it's a good thing to keep in mind as you're doing kinetics, the units that we see associated, again, with the rate constant are really important because it does allow us to figure out oftentimes the type of reaction that we're talking about. Although the first couple here have been second order, they won't always be second order. They could be first order, zero order, or second order, are very common sort of orders of reaction that do take place. Any questions on that particular one there? Okay, so let's take a look at one where you actually do need to use the table here to figure out the rate law. So why don't you take a few minutes here and figure it out. So based on the information provided in the table, you want to determine the completed rate law. So you want to figure out what the rate law is with the orders. You also want to figure out the value of the rate constant. And while you're at it, why don't you figure out the overall order, which shouldn't be too hard. That. So take a few minutes here, use the table information here to figure out those things. Again, stepwise, what you want to do is figure out the orders first, figure out the rate law, and then you can figure out the value of the rate constant. So take a few minutes here and see what you come up with, then we will talk about it. Okay, so let's take a look here. So again, when you're asked to sort of find the completed rate law, the orders, the rate constant, you're given a table like this. Again, that sort of mathematical approach where you basically pick two entries from the table and do the rate 2 over rate 1 approach. Again, when we're looking, we want to find two entries where one of the concentrations remains the same and the other one varies. Again, so we only have really kind of one unknown. We could start with just the generic sort of rate law here, where the rate equals K times our S2O8 minus pad 8 to the X and our I minus to the Y. So again, here the goal is to try to figure out what X and Y is first. So if I go to the table, I can see entry number 1 and number 2. The concentration of the S2O8 is constant, while the I minus varies. So I'm going to put that into the equation there, or the formula. I'm going to choose entry number 1 to put up on top because it has the larger rate, initial rate there. So if I do that, everything from number 1 can go on top. So 2 points. So this is 1 and 2. So this 2.2 times 10 to the minus 4 equals K times 0.08 to the X, 0.034 to the Y. And again, all that is just all the information from entry number 1. Entry number 2 is going to go on the bottom, 1.1 times 10 to the minus 4. We have K and 0.08 to the X and 0.017 to the Y. So here we could do some math. That's going to give me a 2. Again, same idea. K is going to cancel because we don't know what it is, but it is constant. Same thing here. The X's are going to be the same, which means this entire thing will cancel out. And here we will divide, and that will also give me a 2 to the Y. Again, here you could probably just easily determine Y in this case is equal to 1. So the order with respect to I minus is first order. We now want to go back to our table and now find what the other order is. So we want to, in this case, keep the I minus constant and vary our other one because we did the opposite the first time. So if we go to entry number 2 and number 3 here, we see that the I minus remains the same while the S2O8 basically varies. In this case, I'm going to put number 3 up on top since it has the larger rate. So numbers 2 and 3 here. And again, everything for number 3, I'm going to put up on top. And that gives me 0.16 to the X and 0.17 to the Y. And now I'm going to put everything from entry number 2 on the bottom, 1.1 times 10 to the minus 4, K, and 0.08 and 0.017. Missed a 0 there. We'll throw that in there. All right. So when we do the division here, that's going to give us a 4 is equal to, this is going to cancel. 0.08 and 0.16 is giving me 2 to the X. And now that I put the actual 0 that it should be there, these guys will also cancel as well. So this is 2 to the X equals 4. In this case, X should equal 2. 2 squared is 4. Again, you can take the natural log of 4 and divide it by the natural log of 2, and you should get 2 as well. So now we have the actual orders here, and we see that it's not always going to be 1 on both sides. So the completed rate law would be something like the rate is equal to K to the S2O8 minus, and that is going to be second times our I minus, right? So this would be the completed rate law. The overall order for this reaction would be adding those X's and Y's together. So that is 2 plus 1, which means it is a third order reaction. And now that we do have the completed rate law, we can use it to find what the actual value of K is. So we're going to rearrange our rate law down here and solve for K. So in that case, K would equal the rate divided by our S2082 minus squared times our I minus. And just like we talked about, you could choose any entry. You could choose entry number 1, entry number 2, entry number 3, and put it into this expression. And again, because it's the rate constant, it should come out to the same number. You just can't mix and match like we talked about. So we'll take number 1 again here, which would be 2.2 times 10 to the minus 4 molar seconds, divided by our 0.08, which we do need to square, right? Because the order is 2, and times our I minus, which is 0.034 molar. And that's a molar in there as well. And if we do that, we end up with 1.01 or 1. I think that is it, right? That 1, yeah, no exponent. So we end up with 1.0, and the units, molarity here will cancel. Molarity will cancel. There's molarity squared on the bottom, so this would be 1 over molar squared seconds would be the units. Any questions on any of those steps there? You might also notice maybe a pattern here or not. The overall order in the last couple that we did before this was second order, and the units was 1 over molar seconds. So that's like 2 units, right? Molar seconds. This is third order, which is 1 over molar squared seconds. Molar squared is 2 units, and a second is 3 units, which is 3. So, kind of the number of units you sort of see on the rate constant also will sort of tell you, the order as well. First order is 1 over seconds, which is 1 unit. So, that's another way you could kind of figure it out as well. So from a table here, you can see you can figure out a lot of information about a particular reaction. You can figure out the actual rate law. You can figure out the overall order, which is important a little bit later on when we talk about some other formulas, and then also the value of the rate constant. Again, the value of the rate constant, sort of the higher the value of the rate constant, sort of the faster the reaction sort of will take place. So that's one way to sort of think about it. The smaller the rate constant, kind of the slower the reaction will take place. Any questions on that particular one there? All right, so we got another one here. Why don't you try the same thing here? Here we actually have 4 different experiments. So basically do the same thing, figure out the rate law, figure out the value of the rate constant, and figure out the overall order as well. So give it a few minutes here and see what you come up with, then we'll talk about it. Okay, so let's take a look. So same approach here. We're trying to find the rate law. So we could start with just sort of the generic one here, which is the rate is equal to K. Again, just our reactants involved. So our NH4 plus to the X and our NO2 minus to the Y. So in this case, we have 4 entries. And again, you could have a table with 4, 3, 5, 6, however many. But you're going to take really the same approach. So we're looking for, again, 2 entries where one of the concentrations remains the same and the other varies. So in this particular example here, if I take number 1 and 2, 1 and 2 will keep my NO2 minus constant, while it varies my NH4 plus. So if we do 1 and 2 here, number 2 I'm going to put up on top since it has the larger rate, and that is 32.3 times 10 to the minus 7 equals K, and that is 0.06 to the X and 0.2 to the Y. And in case you might have missed it, there is this times 10 to the minus 7 part in the label for the header there on that table. And that means that each of these numbers in this column is times 10 to the minus 7. Good news is on this part of the problem will not make a big difference. If you miss that part, you'll come out the same. Will make a difference at the end. So I'll show you where it really will make a difference. I'm going to put on the bottom here number 1's information, which would be 10.8 times 10 to the minus 7 K and 0.02 to the X and 0.2 to the Y. So at this point, we're going to basically take our top number there on our rate side and divide it. And in this case, you can see you actually don't get a perfectly whole number, but you get 2.99. And the K's will again cancel because they're the same. When we divide this gives us 3 to the X, and these guys will completely cancel. For the most part, you can go, I think that's pretty close to 3, right? And that means that in this case, X is equal to 1. Again, if you wanted to make sure, you could take the natural log of 2.99, and then you could divide it by the natural log of 3, and you'll get 0.9969, which is essentially 1 as well. So you could round in this case to 1, or you could just kind of round it at that point to 3, and you can see you'll get pretty much the same answer there. Technically speaking, it is 0.996, which is essentially 1 as well. So now that we got that order, we then want to go back to our table and choose 2 more entries. And again, at this point, we want to keep the NH4 plus constant. And it looks like our only choice on that is going to be number 3 and number 4, where those guys stay the same. The other one varies. So we'll look at 3 and 4 here. And again, I'm going to put number 4 up on top because it has the larger number. So that gives me 21.6 times 10 to the minus 7 equals K, 0.2 to the X, and 0.0404 to the Y. Down there on the bottom is going to go everything from number 3, which is 10.8 times 10 to the minus 7, K, 0.2 to the X, and 0.0202 to the Y. Again, dividing these guys out gets me 21.6 really divided by 10.8 gives me a 2. Again, the K's will cancel. These guys will cancel because they're the same. Dividing over here gives me 2 to the Y. And again, in this case, Y is going to equal 1. That means that our completed rate law would be the rate equals K NH4 plus to the first power and our NO2 minus also to the first power. And again, you don't need to write the 1s there. It's just implied. Also means that the overall order here would be 1 plus 1, which would be second order in this case. Now we have the completed rate law. We can rearrange it and solve for K. So K in this case would equal the rate divided by NH4 plus and NO2 minus. And just like we talked about previously, you could choose any entry you like to get that. So why not? I'm going to take number 3. We'll just use the information from 3 this time, just to show you that it doesn't matter. And this part, though, in terms of the calculation, is where it's going to make a difference if you did not do the times 10 to the minus 7 part. The other part over here, because this is 10 to the minus 7 divided by 10 to the minus 7, they cancel out. So if you got rid of it anyways here, it would be okay. And when you did like the orders part, but here when you're doing the calculation for K, if you did not include the 10 to the minus 7 part, you are going to be off by that factor. So it will make a difference here. So since I chose number 3, I want to use number 3's information, which is 0.2 here. And 0.02202. And if we do that, 10 to the 8 to the minus 7 divided by 0.2 divided by 0.0202 gives me a 2.7 times 10 to the minus 4, it looks like. So 2.70 times 10 to the minus 4. Units, molarities cancel, leaves us with 1 over molar seconds, which again, if you look at those units, is the same one that we saw previously, also for a second order reaction. So as we'll talk about in the next part of the chapter here, the actual units that are associated with the rate constant is really important. It helps you determine the order of a particular reaction. Any questions on how to figure out the rate law using experimental information there, or the rate constant? Okay, so I think this is actually a pretty good stopping place, so we don't get stopped right in the middle of the next sort of topic. So we will stop here today for lecture. And a couple of reminders. Today, obviously, is our 4th exam. I think 4th exam. So that will be open like all the other ones, starting right around 9:30. In case you want to start a little bit early, you can. If it don't start at 9:30, you should start around our normal lab time, which is 9:45. You shouldn't start hour later or anything like that. You should start between 9:30 and 10 o'clock. Remember, if you start too late, which you should not be doing, you should be starting within that first half hour. You may run out of time and it will not be open for you or anything like that. So same sort of format as before. There will be a multiple choice part up front, which you do not have to obviously show work for. And then there will be a written part where, again, some of the questions will be labeled as to, it needs work shown for those. So for those, obviously, anything that has that work shown for it, you need to show all the work, the units to set up and all that kind of stuff like normal, and including your answer, which should match, again, the answer that you submitted online. There'll be some conversions, and some constants, and some other stuff given to you, I think, in there that you can look at. Also, a periodic table should be given to you as well. Remember that once you complete the exam, you're supposed to upload your work in a very timely fashion. So make sure that you do that as well. There will also be a spot like normal for you to turn in the homework for exam 4, for you to upload that. So make sure you do that today as well, so you don't forget. And I think, remember, it is closed notes, closed book, all that. Nothing of those things should be out, nor should your phone or anything like that. You, again, do need to use Chrome and the Proctorial with your camera on, so make sure you have that all set up. Reminder that it should not ask you for any type of password. If it does, it means you don't have either Chrome or the Proctorial. Something is not set up correctly, so make sure you fix that. You should be able to get in, obviously, doing that. Make sure, other than that, I think that should do it. A reminder, again, you do have some lab reports due tomorrow and stuff like that. So after that, obviously, make sure that you take care of that stuff. We'll continue lecturing tomorrow, and I think we might have the last lab to do, which is a kinetics lab. So by then, we hopefully should have covered enough for you to do that kinetics lab, I think. And that will be it for the lab and stuff like that. A reminder that when you do see your score, again, it's your unadjusted score. It probably will be adjusted something different when I do get a chance to grade those. Any questions on anything like that? If you need me for anything, you can email me through Canvas, but I think everything should be pretty self-explanatory. So, but if there is something, you could email me and we'll get back to you. For some reason you get disconnected from the exam, you can just go back and re-log in. It should be fine. I shouldn't ask you again for anything. You should be able to log back in. A reminder that your timer will not stop, yes, or anything like that. Any questions on anything like that? Okay, so good luck on your exam. If you didn't put here, make sure you put here. And I guess I will see you tomorrow for lecture. So have a good rest of your day. And again, good luck on your exam and all that good stuff.